In the previous video, we have defined elliptic integrals of the first kind, and we used them to express the period of an ideal simple pendulum. And now we are going to define incomplete elliptic integrals of the second kind. And so we see that the definition is closely related to the incomplete elliptic integrals of the first kind, because we just have to take the reciprocal of the integrand to switch between the two. And in this video, we are going to express the perimeter of an ellipse in terms of this integral. So let our ellipse be x squared over a squared plus y squared over b squared equals 1. And we are going to make the assumption that b is greater than a is greater than 0. And we are going to define k to be equal to the square root of 1 minus a squared over b squared. So we claim that the perimeter is then equal to 4b times this complete elliptic integral of the second kind. So the integral from 0 to pi over 2. So the pi over 2 is why we call it complete. And the integrand is 1 minus k squared times sine squared of theta to the power of 1/2. So let us prove this. So we see that we can define a parameter theta to parametrize the points on our ellipse, because when we replace these, we find that it satisfies the equation. And before we proceed, let us just make it clear that theta is not the angle which the line joining the origin to the point xy makes with the positive x-axis if a is not equal to b. And so we see from this diagram that it is related to the angle is related to theta, but it is not actually equal to theta. Anyway, so the perimeter is then given by this arclength formula. So we are integrating from 0 to pi over 2, and then we are multiplying by 4, because the 4 quadrants of the ellipse are symmetrical. So we are only evaluating this length in the formula, and we are multiplying it by 4 to get the total perimeter of the ellipse. And we can differentiate x and y with respect to theta and replace it in this formula. And then we write cos squared equals 1 minus sine squared. And we rearrange and factor out the b squared to arrive at this expression. And we replace this plus by a minus and rewrite and switch a and b in the numerator here. And we see that this is equal to k squared. So where we recall that k was defined to be the square root of 1 minus a squared over b squared. So this shows what was required. And before we end, let us derive a series to evaluate this perimeter of the ellipse, which is similar to the series we obtained in the previous video to evaluate the period of the ideal simple pendulum. So we make use of the binomial theorem to expand the integrand, and then we integrate termwise by making use of this result which we showed in the previous video, which holds whenever n is a positive integer. And when we replace these in the formula here after integrating, we find that we can very nicely express the perimeter of the ellipse by this formula, which can be useful for actually calculating the perimeter.